chapters, these are the harder sections, okay? Section 5, 6, and 7 are the harder sections, so make sure you are paying attention as we go through each one. Today's section is on tangents, okay? So if you did not grab a note sheet, please make sure you do so you can follow along in our notes today. A tangent is a line in the same plane as a circle that intersects the circle in exactly one point. Okay, so this is a line that will only intersect your circle in one specific point. Now that point is called a point of tangency. Okay, so that point of intersection is called the point of tangency. So with your picture on the right there, this line right here, okay, I'll call that line AB. Okay, that line AB is tangent to circle C. Okay, and it's at the point A. Okay, so your point of tangency is that point A where that line AB intersects your circle C. Okay, now being a tangent doesn't mean it has to be a line. It could also be segment AB or ray AB in order to be considered a tangent. Okay, so it doesn't have to be a line. A tangent can be a segment or a ray as well. Now with tangents, we do have common tangents. It is a line, segment, or ray that is tangent to two circles in the same plane. Okay, so we do have two examples of common tangents below. So line L would be a common tangent to circle F and circle G. Okay, so line L intersects circle F here at that point of tangency and circle G here. Okay, so they share a common tangent. In this picture here, this is also a common tangent. Line L is tangent to circle F at this point, circle G at that same point. Okay, so it's that tangent that hits two different circles. So in these next few examples here, we are going to draw in all of the common tangents. So for letter A, I do have two. Okay, I could draw in a common tangent this way. Okay, so that line hits that larger circle at this point and the smaller circle at this point. Okay, the other common tangent in letter A is on the bottom right here. Okay, so it hits the larger circle here and the smaller circle here. Okay, so that one would have two common tangents. Okay, letter B has four. Okay, so one of them could again be across the tops, full circle. Okay, so again, points of tangency for both of those. Where would another one be? The bottom. Okay, so hits the larger circle there, smaller circle here. What about another one? Do you know? Through the middle. Okay, so I hit here and here. And again, there's another one through the middle as well, just in the opposite direction. Okay, so we do have those four common tangents there. Okay, last example on the right, there's only one common tangent. Since you have a smaller circle within a larger, That smaller one intersects at this point here, so that is where your tangent is going to, your common tangent is going to be for both circles. Okay, so again, common tangent is tangent to two circles within the same plane. Questions so far on what a tangent is or what a common tangent is? All right, so the shortest distance from a tangent to the center of a circle is the radius drawn to the point of tangency. Okay, so that's your shortest distance. And that is an important piece. Okay, so your shortest distance from your tangent to the center is the radius drawn to that point of tangency. So in the theorem below, it states in a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. Okay, so again, we're talking about this shortest distance, and it has to be perpendicular. Perpendicular meaning it forms that 90-degree angle. So an example on the right here, line L, okay, that's this line here, is tangent to circle S if and only if line L is perpendicular to ST. Okay, so you can see ST is that radius. Okay, that would be the shortest distance to that tangent. And it has to be perpendicular in order for it to be tangent. If it's not perpendicular and it's less than that or greater than that, that line would not be considered tangent. Okay, so we can use that as perpendicular to determine whether a line is tangent or not. That's what we're going to do in example 1. Okay, so it says segment JL, okay, that's the segment here, is a radius to circle J. We want to determine if KL is tangent to circle J. So we have all of these measurements here. Now in order for KL to be tangent, this has to be a 90-degree angle, right? So what do you see forming there if that would be 90 degrees? What shape? A right triangle. Okay? So since we want this to be a right triangle, I am going to kind of use the Pythagorean theorem to show if this is tangent or not. Okay, so we're going to use this converse. We have JL is 8, KL is 15, and I have this length right here, K to this point, is 9. I'm missing this length right here, but I know what that is. What is that? It's 8. Since JL is 8 and that's a radius, J to this point is also 8 since it's a radius. So I know the entire length of KJ is 17. So now what I want to do is compare my hypotenuse squared to my other two sides squared and add it together. So this is where that converse of the Pythagorean theorem comes into play. Now your c squared value again is always your hypotenuse. Okay, so I'll plug in 17 for C, and then 8 and 15 for A and B. Okay, so I'm comparing those values. So 17 squared is 289. 8 squared is 64. 15 squared is 225. Okay, now I'm just going to add these two together. So I have 289 compared to 289. Those two values are equal. Okay, so since they are equal, that would mean that KL is tangent to that circle. Because since the Pythagorean theorem works here, that means this would be a 90-degree angle. Okay, so I would say KL is tangent to circle J. And I do need you to write this piece out. Okay? And you're proving that is true by your work over here. So you do need to write this out. You don't need to write this part out. But you need to write this out, okay, in order to prove that this is true. Okay, you shouldn't just be saying yes and no for all of these problems. Okay, questions on example 1? All right, I want you guys to do example 2. It's pretty much the same. You can't just go off of looks. You have to use the converse of the Pythagorean theorem. Mm-hmm.
It's only 12 from each little point.
12 is that small section. Yeah. It's not drawn to scale. Relax. All right, most people are finishing up this problem as I walked around. So again, we're determining whether this segment GH is tangent to circle F. Well, for it to be tangent, it has to be perpendicular to that radius drawn in. Okay, so that's why we're using that converse of the Pythagorean theorem. Since my radius is 6, I need to add in 6 to HF here to get that entire hypotenuse side. So I'll take 18 squared, compare it to 8 squared plus 6 squared. Okay, 18 squared is 324. 8 squared is 64. 6 squared is 36. So I have 324 compared to 100. Well, 324 is greater than 100, not equal to it. Okay, since it's not equal, that would mean GH is not tangent to circle F. Okay, so it does have to be equal because this would not form a right triangle then, meaning it does not have that 90-degree angle. Okay, questions on example 2. So that's proving if a line is tangent or not. In some problems, you will be given that it is already tangent and you have to solve for a value of x. Okay, that's what you're doing in example 3. So in example 3, it says JH is tangent, okay, meaning that radius and that tangent segment are perpendicular, and we want to solve for x. Well, again, since it's perpendicular and I have this right triangle formed, I can use the Pythagorean theorem. However, with my hypotenuse here, I need this entire length, okay? Not just this x or this 8. If I look back up here, I had 12 and 6. What did I do to get 18? You add them. So what should this entire segment be?
8 times x.
You need to add them. It's not 8x. That would be multiplying. Okay? You need to add the two together. So, to the left here, we're going to use the Pythagorean theorem. And it does have to be equal now, since I do know that that is already tangent. Okay? So A and B are your two legs. That's x and 12. So we have x squared plus 12 squared is equal to our hypotenuse, which is x plus 8 squared. Okay, if I have this quantity x plus 8 squared, does that result in x squared plus 64?
No.
No. Okay. What this squared means is you're taking this whole quantity, multiplying it by itself. So what you're going to need to do is FOIL.
Oh, like that. What's that mean?
Front, outer, inner, last. So rewrite it as x plus 8 times x plus 8. Okay, it's that quantity multiplied by itself. So I need to take my first two terms, multiply those. So I have x times x. That's x squared. I need to take my outer terms. Okay, x and 8, multiply those to get 8x. Then my inner terms, I need to multiply those two together. Again, that's 8x. And then my last terms, multiply those two together. That's 8 times 8. That's 64. Okay, I can combine my like terms in the middle here. So we have x squared plus 16x plus 64. Okay, that's only that c squared value though, so I need to go back to my Pythagorean theorem now. So back over here, we still have this x squared value plus 12 squared. That's 144. Okay, that's equal to this quantity I just FOILed. So it's equal to this quantity right here. So x squared plus 16x plus 64. Okay, so I just brought this back up here. All right, so from here, we want all of our x's on one side of the equation. Well, if I start with my x squareds, what happens? They cancel each other out. Okay, so I have 144 is equal to 16x plus 64. From here, I'm just going to keep solving for x. So I'll subtract 64. That's 80 is equal to 16x. Divide by 16. Okay, to get x is equal to 5. Okay, questions on example 3. Why I set it up that way, why I FOILed, how I solved it. Okay, again, in this one, yes, Alex?
So why would you FOIL it? It might be obvious.
Why would you FOIL it?
Why would you FOIL it?
Because you have this quantity, okay, x plus 8 squared. What that square does for any term, such as 12, is multiply it by itself. So you need to take this x plus 8, multiply it by itself. Okay, when you have two quantities with addition or subtraction like that, you need to FOIL it. Because if you don't get the correct answer. Okay? So it's just taking that quantity multiplied by itself. That's how you need to think about it. Other questions? All right, then I want you guys to do 3B right here. Okay, you don't have to do 3A, do 3B. Yeah, you're right. All right, looking at 3B. Okay, keep going, I'm sorry. It's okay, I can wait a little bit longer. You've not been here all day. It's first hour.
Yeah, I know.
Gotta push through.
We don't do any.
What? No, you don't have to do it.
Easier one.
All right, so 3B, again, you're given that that segment is tangent. Okay, so QS is tangent. That means that angle made by your radius and your tangent is perpendicular, and it's 90 degrees. Okay, so we can use the Pythagorean theorem in order to solve for x. Well, this length right here, from that outer point on your circle to R is x. Okay, that's a radius. That means QR also has to be x. Okay, so both of those pieces are radius. They have to be the same. I also need the length of SR. I have that smaller section there is 2, and then that x section there. Well, to get the entire length, I need to add those together. This would be x plus 2. So now that I have all my sides of that right triangle, I can use the Pythagorean theorem in order to solve. So my a and b values are my two legs. Okay, that would be x squared plus 4 squared That's equal to this quantity of x plus 2 squared. And again, when you have this quantity squared, you need to FOIL. Okay? So you end up with x squared plus 16 is equal to x squared plus 4x plus 4. Okay, after I FOIL that c value out. Okay, from here, I'm going to subtract x squared from both sides. They do end up canceling out. So I have 16 is equal to 4x plus 4. Subtract 4. You get 12 equals 4x. Divide by 4. And x has to equal 3. Okay, so when you're given that segment or line is tangent to your circle, that means that radius is perpendicular. Okay, it creates that 90-degree angle, so you can use that Pythagorean theorem in order to find side lengths. No. Questions on that part? Okay, sometimes you'll have to prove if it's tangent. Sometimes it's given that it's tangent. You're still using the Pythagorean theorem either way. Okay, the last part here with our tangents then states if two segments from the same exterior point are tangent to a circle, then they are congruent. So in your picture at the right in that theorem there, you have point A is a point of tangency. Point C is a point of tangency. Okay, both of those tangent segments intersect at one point B on the outside of that circle. Okay, so if you go from your point of tangency to that intersection, in both cases, those line segments are going to be congruent to each other. Okay, that doesn't mean the entire tangent is congruent. It's only from that point of tangency to the intersection. So if this extended, okay, if both of these extended out, these two segments would not be congruent. It's just from that point of tangency to the intersection. Now you do have some problems on your assignment where you have a circle inside a triangle like this. And you have to find x and the perimeter of that triangle. Okay? What you would do, if you were given AB is 4, okay, CB would also be 4, right? Now these ones over here, this line is also tangent, okay, to your circle. These two pieces would be congruent to each other. So again, from your point of tangency to that intersection. Okay, so those two are congruent. That means these two are also congruent. Okay, so again, if AB is 4, CB is 4, we'll say C to this point here is 2. That means from this point of tangency to this point is also 2. Okay, and I'll say this one here is 3. That means this one right here is also 3. Okay, so that's how you would do those problems that look like this. Okay? To find the perimeter then, you just add up all of those segments. Make sense?
Mm-hmm.
Okay, then on the bottom, you have 4A and 4B. Okay, we want to find x, and we want to assume that segments that appear tangent are tangent. So in 4A, we have this tangent here, RQ, and this tangent, RS. Okay, from your point of tangency to the intersection in both cases, Those two pieces would have to be congruent to each other. So to solve for x, we can just set them equal. So we have 3x plus 8 is equal to 26. Subtract 8. Three x is equal to 18. Divide by 3. X equals 6. Okay, same thing in 4b. W would be a point of tangent C. Y would be a point of tangent C. Both of those segments intersect at one point outside the circle. Since that is true, those two segments have to be congruent to each other. So I can set their measures equal. So we have 2x plus 9 equals 3x plus 6. Okay, I'll subtract 2x. 9 is equal to x plus 6. Subtract 6. X equals 3. Okay, so you do have to look at your directions for your assignment. Some of them you'll be given that that line is already tangent. Okay, that means you just use the Pythagorean theorem, solve for x. For some of them, you'll have to prove that that line is tangent. Okay, that's the converse. You want to make sure it is equal using that Pythagorean theorem. Okay, and then there's some problems like these ones, okay, where those segments are congruent. What? It's due tomorrow. Any questions?